This is the beginning of our study of circuits. We're going to take a look at in this section what it takes to make a circuit, and we're going to look a little bit at electric potential as well as electric field in circuits. So a couple things you have to have in order to have an electric circuit. You have to have some kind of closed conducting path that goes from the positive to the negative terminal. And you must have an electric potential difference across both ends of the circuit. Remember, an electric potential difference is just a voltage, so relate that to a battery. If a battery has no voltage, you're not going to actually get your electronic device to do anything. You have to have some voltage for it to produce some kind of an effect. So looking at electric potential in circuits, we've got our high potential and our low potential. So we talked about having like parallel plates and things like that last chapter. What we're doing here is we're basically adding a wire. So we're adding some kind of a conducting path. So just like before, we're going to call the positive side is going to be the high potential, and the negative side is going to be the bottom of the electric field, electric hill, or the low potential. So when we look at an electric circuit, you can still define the direction of an electric field based on the direction that a positive test charge would go there. So if we have a battery like this picture, if we put a positive test charge here, it's going to flow away from it. So that's the direction for our electric field, and it's going to go towards the negative. Inside the battery, we'll have an electric field that goes from the positive to the negative. As far as defining our direction for our current and our direction for our electron flow, they're actually going to be opposite, and I'll talk more about this later. But an electric field is defined by the direction of positive test charge, so that's also the direction that the current goes. So in this case, our current is going to go, from positive to negative. Okay, our electrons are actually going to be doing the opposite. The reason for that actually goes back to Ben Franklin. When Ben Franklin did his study on circuits, or really more just on electron flow at that time and current, he didn't know about the electron. The electron hadn't been discovered yet. So he had a very logical explanation for why he thought current flowed the direction that it did, but that's actually something he got backwards. But to this day, we still keep that convention when we talk about the direction that current flows. So I'll mention that more again later, but that is something that does show up in this chapter. So again, we have our positive terminal is going to be our high potential, and our negative terminal is going to be our low potential. So that's how we're defining that direction of current, is from high to low. Okay, this is something that I may be having you do in lab. We're going to take a look at potential as you go through a circuit. So I have a little circuit diagram here in the middle. That's actually called a schematic diagram. This part here represents the battery, and I have the picture below. So for the battery, this would be the negative end, this would be the positive end, so the current's going to flow to the right, and then I have each circle is a light bulb, and the line then is a wire. You'll notice one thing, when they draw schematic diagrams, you always draw them nice and neat with nice little, rectangular looking pictures, where a real circuit might be kind of messy with wires dangling across the place. So they draw the schematic to look neat, but it does accurately still represent the path that the current is going to go through a circuit. So the graph above, then, we're going to look and see what happens to the electric potential, or the voltage, as we go through this circuit. So to begin with, when we go across the battery, the job of the battery is to take something at low potential and crank it up to high potential so it can go through the circuit. So you're going to see a strong electric field there, for one thing, and you're going to see a big increase in potential, which is voltage. When you go through the wires, you see a very small decrease. There's not a whole lot going on in the wires, and think about it this way, there's very little resistance in the wires. That's why we use copper for the wiring in our houses and such, because it has very low resistance. Voltage can travel a long way through wires without really being disrupted. Where you see the big disruptions is in whatever device you put in the circuit. In this case, we're using light bulbs, but it could be your toaster or whatever electrical device you want to use. So what you're going to see there is you're going to see a voltage drop. That's what they call that as you go through the circuit. Each light bulb represents a voltage drop. Again, a small one for the wires. It would, if I did that proportionally, it would even, or to scale, it would even be smaller. And then you would have another voltage drop at the next light bulb. Just for the sake of argument, I made those two different voltage drops. Let's say they were different light bulbs. If they were the same light bulb, they would have exactly the same voltage drop. And then there's that little wire at the end. And I said that about the different light bulbs. Okay, role of the battery. So I kind of already mentioned this, but the whole reason you have to have a battery is to give it the energy. So it's going to be the thing cranking up the charge from low to high terminals, and it's going to give you that delta V, or that electric potential that's going to keep things going through the circuit. So when we talk about energy conversion, so that's what this is really all about, is we're going to use the battery to put energy into the circuit. So the high potential terminal is where you're going to have the most energy. So the test charge is going to go through that circuit, do work on the light bulb. So that means it's actually going to use some of that energy, which again corresponds to that voltage drop that I showed you on the graph before. So it could be a light bulb motor or whatever you're putting the energy into. So as you go through that circuit, you're going to have less and less electric potential, and when that test charge gets back to the negative terminal, then it's down at its low energy again, and it's going to be cranked up through the circuit and used all over again. It's important to note that electrons, or whatever we're calling the positive test charge, I guess is more what we're referring to, that charge doesn't get used up. So by the time the charge gets back to the negative end of the terminal, it's not like the charge isn't there anymore. Charge is conserved just like mass is conserved. So we're not running out of charge, but the charge does have less and less energy by the time it gets to the end. So it needs that battery to give it electric potential energy and start its trip all over again. And that's pretty much it for our intro into circuits.